802.15.4 for my sensors, but those sensors they are not IP enable, so they cannot connect to the internet. Eventually, how my data will go on the cloud? So I have a big problem because I want my data to be accessible from anywhere on my mobile apps that I take it from the cloud. So we have a big issue here. Most of our IoT system, they use IEEE 802.15.4, but this doesn't allow me to transmit the data to the cloud eventually because it is not TCP IP enabled. This is the rationale here. This is where 6-low wireless PAN, this is where this technology becomes very important. Okay, what is the meaning of 6-low wireless PAN? It is IPv6 over low power wireless personal area network. This is the meaning of 6-low wireless PAN. IPv6 over low power wireless personal area network. Okay, so what is this low power wireless personal area network? Is IEEE 802.15.4, and now I'm trying to implement IPv6 over this. So basically, an IP packet. Anyway, we will have it in the future slide. An IP packet is a larger packet, but IEEE 802.15.4, it is a smaller packet. And this technology allows you to adapt. It provides an adaptation layer to fit IPv6 over low power wireless area network. This is what we are trying to make. We are trying to make our IEEE 802.15.4 become IP enabled. Okay, using an adaptation layer, and the name of the adaptation is 6-low wireless PAN. Okay, so this 6-low wireless PAN concept originated from the idea that the internet protocol could and should be applied even to the smallest devices, that is to IoT. IP should be applicable to IoT as well, and that low power devices with limited processing capabilities should be able to participate in the Internet of Things. So basically, not only laptop, PCs, powerful computers, mobile phone, we are talking about small sensors that should be able to connect to the internet and transmit the data to the internet. This is where 6-low wireless PAN technology becomes important. So 6-low wireless PAN has defined encapsulation and header compression mechanism. Okay, so encapsulate data that allow IPv6 packets to be sent and received over. You see here, this is very important. Let me highlight this part is very important here. Allow IPv6 packet to be sent and received over IEEE 802.15.4 base network. Normally, IEEE 802.15.4 base network cannot connect to the internet because they are not IP based. The packets are different, and we have implemented 6-low wireless PAN in order to convert this packet in terms of IP and IP in terms of this packet. This is the adaptation layer which is doing it. So as we proceed, it will become clearer. So low wireless PAN, so it's simple low throughput wireless network. This is what I'm talking about, low wireless PAN here. It is supposed to be low cost and low power. So most of our devices in IoT for wireless sensors and everything, they use low wireless PAN. That is 802.15.4, IEEE 802.15.4. And common topologies that they use star. Okay, a number of nodes connected to a central node, or mesh. Each node connects to each other, or a combination of star and mesh. Okay, and I have already mentioned you the physical and the MAC layers. What they use, they conforms to IEEE 802.15.4. This is what they use. But I know that this one is not IP enabled. This is a typical low wireless PAN architecture. We're talking about low wireless PAN and not 6. There's no 6 here. But the low wireless PAN, this is how it operates. This is a star topology where your sensors communicate to some gateway, to some node here. And then this is a peer-to-peer mesh one, okay, where you have such kind of communication. Each node can communicate to all the other nodes in a peer-to-peer fashion. Okay, so now, and you see the packet. Here is the packet. What do we have? The different, the MAC payload, the frame payload, the packet. This is a typical 6-low wireless PAN a packet, which is different from an IP packet. So now the 6-low wireless PAN characteristic, what it is supposed to do is small packet size, is 16 bit short, okay, and it is low bandwidth topologies store and mesh. It uses. It is low cost, okay. Networks tend to be ad hoc, inherently unreliable due to the nature of the devices that can have connection and or not. So there are a number of assumptions for this technology. Devices conform to, we are using IEEE 802.15.4, okay. Devices typically send small amount of data. We don't transmit large volumes of data. And we are talking about constrained devices, both in terms of computing power, in terms of energy, in terms of cost, in terms of memory. They are constrained. So for this situation, we use, so for this situation, what is the problem? I've already explained this problem. No method exists to make IP run over IEEE 802.15.4. This is our problem, because we don't have a mechanism to allow this. And you see here, a IEEE 802.15.4, a PDU, the how do you call it? Data units, the packet data units. It is of 81 octet. It is its size. Its size is so much, whereas an IPv6 normally is 1,280 octet. Okay, so stacking IP and above layers as is may not fit within one a IEEE 802.15.4 frame. So these two, one is larger, this one is smaller. So how you can make one fit in the other? So this is difficult. Okay. Not all ad hoc routing protocol may be immediately stable for this low wireless span. So all the routing protocol that we have used on Ethernet, even on our wireless network, normal wireless network, Wi-Fi, anything, will fail here because they will not fit the packet size and anything. For example, DSR, ODV, or routing protocols that will not be directly applicable for a network that is IEEE 802.15.4 network. So current a service discovery, they are too bulky to be applicable to PAN, to low wireless PAN. So all these are problems why these networks, IoT networks that is using IEEE 802.15.4, why they cannot connect to the internet, why it will be difficult for them to be able to use TCP IP. But obviously with the solution is 6 low wireless PAN, as we are going to see in a few seconds. So goal, we need to define an adaptation. And here we're talking about solution. Here were the problems. Okay, here is the solution. Okay, so define an adaptation, the layer to match IPv6 the requirements. So fragmentation, 1,280 bytes for IPv6 should be mapped into 127 bytes for IEEE 802.15.4 frame. So we need to be able to convert this. So specify methods to do IPv6 stateless address auto configuration. This is required. Use header compression. Specify implementation content and best method for IPv6 stack on this type of network. This is where the 6 low wireless PAN is doing all this. Adapt network management, specify encoding and decoding for discovery. So the 6 low wireless PAN should do all this. Here is the solution. Okay, you see here, this is TCP IP, normal TCP IP. This is 6 low wireless PAN. You see down what it used at the physical layer. It used IEEE 802.15.4. Then there's an adaptation layer here at the network level, IPv6 with 6 low wireless PAN, and above it it uses UDP, and then here it becomes IP based. What makes it become IP based? It is this adaptation layer that is converting the 802.15.4 to TCP IP above. Okay, this is a simple architecture. So how it works, you have your sensors, whatever, that is connected to what is called an edge router. An edge router connected to a normal router, which allow connection to the internet. This is an extended, where is the word here? Multiple edge. It's extended low wireless PAN. You have multiple networks connected to edge routers and routers connected to router, which allow us connection to the internet eventually. So at the end of the day, here we're using IEEE 802.15.4. But at the end of the day, the data is being converted and pushed over the internet. This is the solution for sending sensor data to the internet. Okay, so 6 low wireless PAN implementation exists for both. It operates at high frequency 2.4 or even low frequency in the range of 900 megahertz. Okay, so 6 low wireless PAN offer the advantages of 802.15.4, that is, can form mesh network and anything, and it is low power consumption. This is a mandatory requirement anyway for our IoT network. Combined, what is the added advantage here? Combined with the benefits of IP communication, it allows you connection to the internet. Okay, so it is a popular proven open source 6 low wireless PAN. A particular technology that has implemented 6 low wireless PAN is called Contiki, the Contiki open source operating system. It uses directly 6 low wireless PAN. A Contiki is an OS that many boards, many IoT system they use this operating system. Okay, so we have seen Bluetooth, we have seen Z-Wave. Very important, we have seen 6 low wireless PAN. The 6 low wireless PAN allow us this conversion from IEEE 100.15.4 to TCP to IP based for our data to be able to go to the cloud. Okay, now let's move on to this is actually Thread. Thread is a communication technology that this is the technique we use, 6 low wireless PAN. A specific technology that have implemented 6 low wireless PAN is Thread. Thread is a technology that is based on 6 low wireless PAN. So Thread is an effort of over 50 companies, or even Google and those popular companies there, to standardize on a protocol running 6 low wireless PAN to enable home automation. Have devised this protocol mainly for home automation. Okay, so it is an IPv6 based low power mesh networking technology for IoT products. So most often, if you're buying some IoT sensors for home or whatever, it may be using Thread already there. Okay, so Thread uses 6 low wireless PAN, which in turn uses IEEE 100.15.4. You see here, it's based on 15.4, but eventually the data goes to the internet. Okay, and as does ZigBee and other systems. So Thread, however, is IP addressable. ZigBee is not IP based. ZigBee short distance communication, but here, what is advantage of Thread? Thread allow you connection to the internet as well. Okay, it works on the sensors, plus it allow you transmission to the internet with cloud access and AES encryption as well already provided them. So I've told you about Google, Samsung, and a number of all those big players. They are currently promoting this technology. Low power IoT nodes to IP network form the Thread group to define a standard that ensures device interoperability throughout your devices can communicate with each other very easily. So Thread appears to have established itself, as a future for IP. You see here, this is I highlight this. IP over 802.15.4 compared to ZigBee IP, which has not got lots of popularity. Instead, this technology is getting lots of popularity. That is Thread, that is IP over IEEE 802.15.4. So it provides data rates of up to 250. So not high data rate, but we don't require high data rate anyway for IoT system, and it can support around 250 devices in one network. You can extend it by having other network as well. Okay, so this is Thread. Okay, so I think we will have time to tackle this one as well. Let me check. We have reached. Okay, we have time to proceed to this one as well. Okay, so up to now, we have seen Bluetooth, we have seen Z-Wave, we have seen even 6 low wireless PAN and everything. We were dealing with, up to now, most of the technologies were short distance communication technologies. Okay, they allow you short distance communication. Obviously, 6 low wireless even convert the packet into TCP IP. So, but the communication there, it is still short distance. So if over my sensors, they are deployed quite far from my edge node or from my gateway, from my router or whatever, they are quite far. So in this case, I will have to transmit the sensor data itself. I'm not talking to the cloud, but to a gateway which is quite far in terms of kilometers. Okay, you may have your sensors deployed in a city or whatever. You won't be able to make each of your sensor become IP enabled where you are transmitting it directly to the internet. So you will need to send it eventually to some gateway, which will be quite far, and then eventually the gateway communicate to the internet to transfer the data to a cloud platform. So we do require long distance communication as well. Okay, so one type of long distance communication is what is called sub 1 gigahertz RF. This is not a technology, this is a specific technique that we use, and you have many technologies that have implemented this this technique. Okay, so sub 1 gigahertz RF operates in the ISM spectrum band. So why it is called sub 1 gigahertz? So you know your Wi-Fi operate in 2.4 gigahertz, that is more than 1 gigahertz. Here we are talking technologies that uses frequency which is less than 1 gigahertz. This is why it's called sub 1 gigahertz. That is technologies that operates at a frequency which is less than 1 gigahertz. So it's what it says here. Typically in the 700, 900 megahertz, 300 megahertz, 400 megahertz. So which is less than 1 gigahertz frequency range. What is the advantage after we get when we use a lower frequency? Earlier I have said something. Yeah.
Cover higher area, larger areas.
Yeah, longer distances. We cover longer distances. When you use lower frequency, the wavelength of that frequency, they are longer. So in one cycle, they cover a long. This is I don't know whether you're able to see my video. You're able to see me on the video. So if yes.
Yes.
Okay. So if it is a higher frequency, the signal is like this. This is a higher frequency. It do lots of pattern, lots of cycle in 1 second. If we use a lower frequency, it is like this. A lower frequency is like this. Higher frequency like this. Lower frequency is like this. So which one is covering longer distances? The lower frequency is covering longer distances. The wavelength is covering longer distances. The higher frequency, it is moving, but it is moving very short distances. So this is the relationship that exists between high frequency, shorter distances, lower frequency, longer distances. Okay, maybe we should do an analogy, a comparison with data rate. There are two things we look when we talk about a communication technology. I already said this is a signal 2.4 gigahertz. It is like this, 2.4 gigahertz. This is 2.4 gigahertz. Actually, I can give you the exact length of Wi-Fi, 2.4 gigahertz. If I'm not mistaken, it is something like 12 centimeter to 15 centimeter. That's long, a Wi-Fi signal. Okay. Now if we're using a longer frequency, that is a lower frequency. It is like this. So tell me, this is distance. What I have to do? Higher frequency means shorter distance. Lower frequency means longer distance. Tell me what relationship exists between higher frequency with now data rate, not distance but data rate, and lower frequency with data rate. What do you think? Anyone in the class? Higher frequency, what type of data rate it give you? Lower frequency, what kind of data rate it give you? Anyone? Which one give higher data rate in terms of megabits per second, whatever?
Higher frequency.
Wi-Fi.
Okay, say it again. I've heard two answers at the same time.
High frequency.
High frequency give you?
High data rate.
Higher frequency give you higher data rate. Yes, true. High frequency, after it travels short distance, it cannot go very far. But the good thing about high frequency, it carry more data for you. So this is zeros and ones. So it is oscillating very fast. So it carry more data for you. Whereas lower frequency, this means A0, A1, A0, A1. So it is carrying less zeros and ones for you. So the data rate is less, but it is covering longer distances for you. So this is a relationship that exists between frequency with distance and data rate. So here, what are we talking about here? Here we're talking about sub 1 gigahertz RF, that is lower frequency signals. Okay, lower frequency signal. So obviously, what we get with it, we get longer distances, and data rate is not an issue for us because we are talking about IoT. IoT has not got a lot of large volume of data, small amount of data, but very frequently. So it is small amount of data still. So you see here. So this spectrum band below 1 gigahertz is particularly useful for RF IoT application. So application of IoT are typically low power, okay, and offer several advantages over 2.4. 2.4 is Wi-Fi, okay. So here we get lots of advantages by going for, excuse me, lower frequency. Here are some advantages. The range is very long, okay. Sub 1 gigahertz offer more range than 2.4. The range is important criteria. If you want to transmit longer distances, some sub 1 gigahertz will give you something. You see here, what kind of distance are we talking here? We're talking about 100 kilometers. Not only a few meters, not 1 kilometer, not 2 kilometers, very far. It can carry your data very far, 100 kilometers. It is still low power, okay? Needs a low power signal for the transceiver compared to 2.4 gigahertz. And also one another very important advantage of sub 1 gigahertz is that since the wavelength, since the signal is low frequency, it is less affected by interference. Higher frequency signal, they are more affected by interference. Interference means anything: walls, vehicles, trees. When it is raining, all these interfere with our signal. And low frequency signal, they are less affected by noise. They are less affected by obstacle, by interferences. This is very important. Okay, let's continue. So sub gigahertz technology is an ideal choice for wireless application requiring long distance, low power. So what do we get with sub gigahertz? We get long distance, and it is still low power. So very good candidate for IoT. Very good candidate for long distance transmission and low power transmission. So narrow band transmission can transmit data to distance hub quite far, often several miles away. We have seen in terms of 100 kilometers without hopping, without transmitting. Hopping, one node transmitting to another node transmitting. When you cannot transmit very far, this is what you should do: hop one node to another node, another node to another node. But when you do this, you consume lots of energy of the node. So instead of this, if you can have one long distance communication, then it will be very good. So this long range transmission capability reduces the need for multiple expensive base stations. So you cannot put the base station close to each of your sensors because your communication technology is very short. You will have to place many of those base stations. So here you can place one base station in port list, and all your sensors around port list goes to that one base station because you are implementing sub 1 gigahertz a technology, okay, which allow you long distance communication. Now, specific technologies that are considered to be sub 1 gigahertz RF are LoRaWAN. Earlier we mentioned about LoRa. SigFox is another one. It's a special kind of IEEE 802.11 is what? 11 is what? Anyone in the class? IEEE 802.11. Which technology are we talking about?
Wi-Fi.
Exactly, it is Wi-Fi. But here we're not talking only about 11, we're talking IEEE 802.11 AH. AH is another kind of Wi-Fi. Just like for Bluetooth, we have classic Bluetooth and BLE. Even Wi-Fi now, there is a new version of Wi-Fi that has been proposed, okay, for IoT. Okay, I don't know whether, have you heard about Halo? Wi-Fi Halo. This is a special kind of Wi-Fi, okay. Obviously, it can transmit long distance and it consume low power. So for IoT, it's very good if you can have long distance and low power, okay. So all these, what to tell you, all these technologies they uses sub 1 gigahertz RF. And we have just seen the advantage of sub 1 gigahertz RF. Now here it is, the IEEE 115AH. AH is a wireless networking protocol published in 2017, quite recent. Okay, instead of Halo, it is written Halo. You see here Wi-Fi Halo, but it is pronounced Halo. Okay, Wi-Fi Halo. Okay, so it uses 900. 900 is less than 1 gigahertz. Okay, compared to the conventional Wi-Fi that uses 2.4 and 5 gigahertz higher frequency. This one is using lower frequency, and you know the advantage we get when we use lower frequency: longer range, less interference, longer transmission range, is travel further. It also benefits from low energy consumption. Another characteristic, it should consume less energy because it is going to be used in IoT system, allowing the creation of large group of stations and sensors that cooperate to share signal, supporting the concept of IoT. This is why it's a good candidate. This is why it was invented anyway, quite recent. Okay, IEEE 802.11AH, a new version of Wi-Fi. Okay, the protocol's low power consumption competes with Bluetooth, so it is competing even with Bluetooth. Normally, Wi-Fi consumes lots more energy than Bluetooth, but here we have a technology, a new Wi-Fi that is competing with Bluetooth in terms of energy consumption and added benefits of higher data rates. It is able to give us some reasonable data rate, and see all the advantages are summarized in this point here. Free advantages. I can see free advantages here. Let's have a look at this here and tell me what are those free advantages. Laura, Niaviti, Laura, what are those free advantages that you can see in this point for this new Wi-Fi, IEEE 802.11AH instead? I see free advantage here. Let me check if you are on chat. Yeah, Laura. Niaviti, Laura. Yes, I see you on chat. Tell me what advantages you see on this slide or this new version of Wi-Fi that we require in IoT. It consumes less power, first. Second, consume less power, yes, true. Second, I'll show you the slide again. Yes, I don't see your answers. Allow connection of large groups. Okay, we can say this is an advantage. But on this point, there are two other advantages I see here. Anyone else? Let me check. Someone have not. Sigulam? Yuvraj? Sigulam?
Yes.
Yuvraj Sigulam? Yes. So on this slide here, your friend already said low power. What are the two advantages you see here?
It can send more data per time.
Okay, higher data rates. Okay, more data per unit time. The data rate is higher. Okay, next.
And it has greater distance coverage.
Okay, it can cover longer distance. Okay, good. So those three, you see here, this version of Bluetooth has got all these advantages, and all these are important for IoT. Low power, data rate is good, and it travel long distance. So this is why this technology, it's quite recent. So we need to see how it evolves with respect to whether sensors manufacturers, they will be using more and more of this technology. We need to do follow up and see what is happening with respect to this. technology. You see here the IEEE 11AH is a new Wi-Fi standard that operates in the sub 1. Now you understand what is this sub 1 gigahertz region. It is less than 1 gigahertz. Wi-Fi normally uses 2.4 gigahertz. Here we are talking about a new version of Wi-Fi that is using 900 megahertz, which is less than 1 giga. And you can see here, different countries use different frequency range. In China, it is in the range of 700. In USA, it is 900. In most, like in Europe, it is in the range of 800. Otherwise, in the other countries, it is in the range of 900. So this technology, this standard, okay, defines channels based on the spectrum in the given country. So each country, they choose which frequency they are going to allocate for 802.11ah. Okay, why the channels are available? So if you want more bandwidth, so normally it uses 2 megahertz channels. Otherwise, 2, 4, 8, 16 megahertz can be used as well. And the MAC layer, yeah, the medium access control for 802.11ah features a number of enhancements, okay, compared to normal Wi-Fi. First of all, it supports a large number of stations, so more devices can be connected. You can read it here. Access point allocate identifiers, so it uses a hierarchical approach. Check, yeah, it's hierarchical association identifiers here. Okay, a hierarchical approach where you can a maximum number of 8,191 stations you can identify when you're using this AH version. Now for power saving, it's a growing issue. So especially in AH, it uses for many IoT. So many remote will need to run using. So it uses what is called here. So it needs to run for weeks or even years. So these stations, we call it team station, remain awake all the time, can really monitor the beacon frames that are sent. Okay, here it's a mechanism to save energy. Throughput in terms of data rate mainly. Okay, so in order to be able to make the best use of available bandwidth, okay, a number of enhancements here carried out so as to transmit the data in an efficient manner. For example, has proposed a new MAC header that is more compact, so lesser in terms of the amount of information that you're transmitting is lesser, so as you can transmit more of your data. So all these are advantages of using the AH, the IEEE 802.11ah. Okay, so let me not discuss LoRa. LoRa, I will discuss it next time. The second part of this lecture will continue next time. So we are discussing our chapter 4 on access technologies. You have noticed we have discussed a number of short-range technologies and a number of long-distance technologies. Very important, LoRa and SigFox that we will discuss in our next lecture for this module. Note that next week we are not having our lecture on Monday. Okay, it will be subsequently replaced, but otherwise we'll have our lecture the following week on Monday, where we'll wrap up this chapter. Okay, after this chapter we have only we will discuss some application areas, and we will be wrapping up because for this semester, even in by December, we will be still in week 12, because this semester will continue in January, February. Okay, so we still have time for the remaining part of this module. And in the lab, very important, we are doing important lab on the microcontroller, so as to give you the necessary experience, competence that you require for your mini project. Okay, so any question from class on what we have discussed today? The class test, which has been forwarded to 3rd of December. Yeah, 3rd of December. So I'm still keeping the coverage of the class test. I won't be giving you access technologies. Okay, everything that we have discussed before will be covered in the test. and not access technology that we are discussing now. So recall all about the sensors, type of sensors, about the actuators, about IoT platforms will be there. Okay, everything that we have discussed up to and including IoT platform will be there, and access technologies will not be there. Okay, any question from students about this lecture? Let me stop recording.